Good afternoon. My name is Fabio Gonzalez, and I'll be presenting our final chemistry project alongside my partner Donovan. So first, we're going to go ahead and apply Hess's law to a chemical problem. And so first of all, remember that Hess's law states that related reactions can be added to get the heat of a larger reaction. And this is possible since enthalpy is a state function, meaning only the beginning and end matter, not what happens in between. So the question we're given is, what is the enthalpy of reaction with methane? And then it gives us a balanced chemical equation for it. So to solve this problem, we're going to have to use the equations given to us. And the equations given to us are number 1, 2, and 3. So first, we also observe that we're given the enthalpies of formation for each equation, which are going to be used in order to find the total enthalpy of formation, the methane. So first, we're going to use equation 3, and we're going to flip it since we need methane in the product side since we want to produce methane. And then we go ahead and use the first equation afterwards. And we're going to take in consideration that we're going to be adding all these equations together. So then after using the third, we go ahead and take the first equation, which is the hydrogen equation, and then we're going to double the whole equation. Since we see from our balanced chemical equation for the formation of methane that we're going to need a total of 4 hydrogen, and that equation only gives us 2. So we're going to add a coefficient of 2 in front of all of the reactants and products of that equation. All right, so thirdly, we go ahead and grab the second equation, and we can leave it as is, since it's going to give us what we need. So when we go ahead and add them, we see that that the products and the reactants in all the equations are going to add up and cancel out to give us our main equation that we want, the formation of methane. So then also something we want to do is go ahead and look at the enthalpies of formation for each equation. So for the third equation we used, when we add them together, we go ahead and change the negative sign, its original negative sign, to a positive sign since we flipped the equation. This means that it's consuming energy, and we see it's 890.3 kilojoules per mole. And then for the next equation we used, remember it was a hydrogen equation, and then that one we doubled, so we're going to have to double the enthalpy of formation since we're producing double the amount of products, and that's going to give us negative 571.6 kilojoules per mole. And then for our third equation, we see that we can just leave it as is because we didn't change anything about it. So that's negative 393.5 kilojoules per mole. So then we go ahead and add all these up, like we did with each chemical equation that we added up. And when we add up those enthalpies of formation, we get negative 74.8 kilojoules per mole, and that's the enthalpy of reaction of methane.
We will discuss how to find empirical formula from combustion analysis. So combustion reactions generally look like this. So we have a compound made up of carbon, hydrogen, and oxygen that will react with oxygen to form CO2 and H2O. So we'll be finding the mass of carbon from CO2, the mass of hydrogen from H2O, and the mass of oxygen in the original compound by subtracting carbon and hydrogen. So for our first example, there's 14.77 grams of a compound that produces 43.26 grams of CO2 and 12.4 grams of H2O, and we must find the empirical formula. So first, let's start off by finding grams of carbon from CO2. So we will do this by converting grams of CO2 to moles of CO2, which we can use to find moles of carbon and then convert to grams of carbon. So we have 43.26 grams of CO2, and we multiply by 1 mole of CO2 over 44.004 grams of CO2 times 1 mole of carbon for every 1 mole of CO2 times 12.011 grams of carbon over 1 mole of carbon, and we get 11.81 grams of carbon. Now to find hydrogen from H2O, we'll be following similar steps. So we have 12.4 grams of H2O times 1 mole of H2O for 18.015 grams of H2O times 2 moles of hydrogen over 1 mole of H2O times 1.0079 grams of hydrogen over 1 mole of hydrogen, and we will have 1.388 grams of hydrogen. Now we can find grams of oxygen in the original compound by subtracting hydrogen and carbon. So we have 14.77 grams of the original compound minus carbon, which is 11.81 grams, and hydrogen, which is 1.388 grams, and we get 1.57 grams of oxygen. Now, if we want to find the empirical formula, we must convert to moles and divide by the smallest mole. So we have first for carbon, 11.81 grams of carbon times 1 mole of carbon over 12.001 grams of carbon, which gives us 0.9833 moles of carbon. Then we have 1.388 grams of hydrogen times 1 mole of hydrogen over 1.0079 grams of hydrogen, and we get 1.377 moles of hydrogen. Then for oxygen, we have 1.57 grams times 1 mole of oxygen over 15.99 grams of oxygen, which will give us 0.0981 moles of oxygen. And then we divide all of these by the smallest mole, which is 0.0981. So for carbon, we have 10, hydrogen we have 14, and for oxygen we will have 1. So that will give us C10H14O1. And that will conclude finding empirical formula from combustion analysis.
Now let's move on to connecting some microscopic properties to macroscopic behaviors. And specifically, we'll be talking about intermolecular forces and how they affect the substance's solubility and boiling point. So let's just have let's take a quick flashback to what are intermolecular forces. And there's three main intermolecular forces. We have London dispersion forces, in which temporary dipoles created by compounds and molecules creates an attraction between both of them due to the opposite charges, and these are the weakest. Then we have dipole to dipole bonds, in which the polar molecules, or remember that there are the differences in electronegativity means that there's going to be a slight positive and a slight negative end, and so we have those two slight charges attracting the slight charges of other molecules or compounds, and those are dipole to dipole interactions. And also remember that hydrogen bonds are a type of dipole to dipole interaction, which is stronger than other dipole to dipole interactions. And then thirdly, we have ion to dipole interactions, which involve the former dipoles we're talking about in polar molecules, and a charge and an ion attracting one another. And this is the strongest since we have a complete charge and a partial charge. So now let's talk about how that influences a substance like a solid solubility and boiling point. So in terms of boiling points, a stronger interaction means a higher boiling point. So that means that the more polar molecules are, that means they're going to have a higher boiling point, since more polarity means that partial charge is going to be greater and the attraction is going to be greater. And the same logic applies to ion to dipole interactions. So the higher the ionic charge or the partial charge, the higher the boiling point, since those bonds are going to be stronger. And then the graph gives you a little example of how the dipole moments influence the boiling point by through a correlation where increasing dipole moment increases boiling point. In terms of the solubility, well, we have a fight between those interactions and the interactions with, in this case, water. So let's go to ionic compounds. So here we have ion to dipole interactions versus the lattice energy of the lattice. So the ion to dipole interactions are occurring between the water molecules and the ions. Since remember the hydrogen bonds, there's going to be an attraction there, and they're going to be pulling on the ions in the lattice, and they're going to form a hydration circle or hydration sphere, where there's going to be a multiple of the water molecules pulling on the ions, and whether they can override that lattice energy and will determine whether the ions will be pulled apart and the compound will be dissolved. So for polar molecules, again, the same logic applies. We're going to have the dipole to dipole interactions in the compound going against the interactions between the solvent and the solute. And then so if the interactions between the solvent and the solute, whether they're dipole to dipole or hydrogen bonds, are stronger than the dipole to dipole interactions in the compound, will determine whether the substance or solid is dissolved. Also, really quickly, remember that nonpolar compounds or substances can't dissolve in polar because the interactions are different. And nonpolar, we're going to have a similar thing happening, except it's going to be a fight between London dispersion forces in the compound and between the solvent and solute. So it's like comparing nonpolar and polar substances is like comparing apples versus oranges. So that's why nonpolar substances can't dissolve in polar substances.
Now we will discuss phase diagrams and the unique and unusual properties of water. First and foremost, what is a phase diagram? Well, a phase diagram is a graphical representation depicting the physical states of a substance under different conditions of temperature and pressure. So why specifically are temperature and pressure chosen? Well, the pressure that surrounds a substance can affect states of matter because pressure applies forces on substances which allow them to be more compact and held together. So when the pressure increases, more energy is required and freezing and boiling points increase. When temperature increases, molecules and atoms have more kinetic energy and allow substances to more readily change state from solid to liquid or liquid to gas. Now if we take a look at a phase diagram, we can see that it is divided into the three states of matter: solid, liquid, and gas. Then we have the triple point, which is the point where the temperature and pressure where a substance can coexist as a gas, liquid, or solid. Then we have the critical point, which is the point where the two phases of a substance cannot be distinguishable from each other. This is where density of a liquid and vapor are equal and thus form a supercritical fluid. Now onto the special properties of water. Because of the hydrogen bonds that exist in water, water has a large boiling point. This is because a large amount of energy is required to break those hydrogen bonds before water can freeze or boil. As a result of water having such a large range to exist as a liquid and can be very slow to freeze or boil, it allows ecosystems to thrive. If water was very easy to freeze or boil, drastic changes in the environment, such as oceans or lakes, would cause all the organisms living in the water to die. Then there is surface tension. Water has high surface tension due to its hydrogen bonds. This allows things to be placed on the surface of water despite density. Many organisms, such as insects, use surface tension to walk on water without sinking. These organisms are able to do so because the force they apply on the surface of the water is not enough to break the hydrogen bonds of surface water molecules. Water also has a high heat of vaporization. This property of water is beneficial to the ecosystem because it helps moderate the temperature of the ecosystem. The quantity of heat that is required to convert a unit of water into its vapor form is very high because of the hydrogen bonds found inside water. Then there's viscosity. The viscosity of water measures its resistance to flow and is critical to many of its functions. The low viscosity of water is important in its role as a solvent for life's chemicals reactions and for blood circulation. Water's cohesion, which are the attractive forces that allow molecules to stick together, also make it unique. The cohesion of water molecules helps plants take up water at their roots through capillary action and helps animals regulate body temperature. Water is also a universal solvent. Because of water's polarity, it is able to dissolve or dissociate many particles. Oxygen has a slightly negative charge, while the two hydrogens have a slightly positive charge. The slightly negative particles of a compound will be attracted to the water's hydrogen atoms, while the slightly positive particles will be attracted to water's oxygen molecule. This causes the compound to dissociate. Finally is water's density. For all substances, they become less dense when they are heated and more dense when they are cooled. However, water only continues to become more dense until it reaches 4 degrees Celsius. After it reaches 4 degrees Celsius, it will become less dense. When freezing, molecules within water begin to move around more slowly, making it easier for them to form hydrogen bonds and eventually arrange themselves into an open crystalline hexagonal structure. Because of this open structure, as the water molecules are being held further apart, this makes water's liquid state more compact than its solid state and explains why ice is able to float on water. Ice at the top of a body of water serves as an insulator and allows life in water to survive. And that will sum up phase diagrams, states of matter, and the properties of water.
Alright, now let's go ahead and discuss a chemistry lab scenario. So for this one, we'll be discussing how to calculate the heat of combustion in a chemistry laboratory for sucrose. So the main equipment needed is going to be a palm calorimeter, a balance, and weighing paper. So first, let's go ahead and discuss the procedure. So first, we're going to go ahead and weigh the sucrose on the balance to make sure to tare the balance first. And then we're going to record that weight. Afterwards, we're going to allow the palm calorimeter to run for 20 to 30 seconds in order to reach a baseline temperature before placing the sucrose in the calorimeter and igniting it. Afterwards, we place the sucrose in the bomb calorimeter and ignite the sucrose. Again, we're going to have to allow the calorimeter to run for some time, in this case 5 minutes, in order to let the temperature to level off. Finally, we're going to record the initial and final temperatures, since they're going to be crucial in calculating the heat of combustion. So now let's assume that we're given that the heat capacity of the system is 10.310 kilojoules per Kelvin, and then we measure that the sucrose sample mass is 0.9982 grams, and the initial temperature is 298.143 Kelvin, and the final temperature is 299.756 Kelvin. Alright, so assuming this, we can go ahead and go into solving for the heat of combustion of the sucrose. So first of all, remember that the heat of combustion of sucrose is equal to the heat capacity of the system times the change in temperature all over the number of moles. So that means that we're first going to have to convert our grams of sucrose to moles. And it's given in the equation right there. So we have 0.9982 grams of sucrose, and we're going to multiply it by the molar mass of sucrose. So we're going to multiply it by 1 mole of sucrose over 342.3 grams of sucrose. This gives us the amount of moles, which is 2.92 times 10 to the negative 3 moles of sucrose. Afterwards, we calculate the change in temperature. So we subtract the final minus the initial temperature, we get 1.613 Kelvin. Finally, we just go ahead and plug in all the numbers into our equation, which gives us 5,695.2 kilojoules per mole for the heat of combustion of sucrose. And then we can go ahead and calculate the percent error. So let's say that the standard value for the heat of combustion is 5,639. So we go ahead and subtract that from our value, which is 5,695.2 kilojoules per mole, and we go ahead and divide all that by the accepted value, which is again 5,639 kilojoules per mole, and multiply that by 100 to get a percentage, and this gives us 1%. So we have a pretty low percent error. Still, there is some potential sources of error, and these can include inadequate calorimeter installation, which can let some heat escape and therefore can change our value for the heat of combustion, or also there could have been incomplete combustion of the sucrose. So an incomplete combustion of the sucrose would mean again that it would change our value for the heat of combustion of sucrose.
Finally, we will discuss our electrolyte lab. Electrical conductivity is a result of the movement of electrically charged particles known as electrons. When electrons are allowed to move freely throughout a substance, the substance can conduct electricity. A substance that produces an electrically conducting solution when dissolved in a polar solvent such as water is known as an electrolyte. Ions carry the electric charge to the solution, thus creating an electric current. Substances that are highly ionized are also strong electrolytes. Strong acids and salts are strong electrolytes because they completely ionize in solution, meaning that they dissociate and separate. One example of an electrolyte is sodium chloride. Ionic compounds cannot conduct electricity when solid, as their ions are held in fixed positions and cannot move. Despite both solid sodium chloride and liquid H2O being non-conductive, when combined to form an aqueous solution, it can conduct electricity. This occurs because when suspended in H2O, ions in sodium chloride dissociate and allow electrons to flow freely. This allows the solution to conduct electricity. A strong electrolyte is a solution or solute that completely or almost completely ionizes or dissociates in a solution. A weak electrolyte is an electrolyte that does not completely dissociate in aqueous solution. The purpose of this lab was to observe the electrical conductivity of substances in various aqueous solutions, to differentiate between strong or weak electrolytes, and to interpret a chemical reaction by observing aqueous solution conductivity. In the lab, various aqueous solutions containing sodium chloride, sodium carbonate, sodium bicarbonate, potassium nitrate, and ammonium chloride, ammonia, hydrochloric acid, and hydrogen cyanide were tested for their electrical conductivity. This was accomplished via a conductivity probe and meter. The substances were then categorized as a strong or weak electrolyte. The required equipment for this lab are a balance to weigh the samples, beakers to form solutions, a conductivity meter to record the conductivity of the solutions, a graduated cylinder, weighing paper, and of course samples of the reagents. So the procedure of this lab. First, we started by weighing a 1 gram sample of sodium chloride, recording the weight and placing that sample into a beaker. Then, a graduated cylinder was used to measure and pour 25 milliliters of water into the beaker containing 1 gram of sodium chloride. Next, a conductivity meter and probe were used to measure the electrical conductivity of the solution. This was recorded in a data table as well. The previous steps for sodium chloride were also then repeated for sodium carbonate, sodium bicarbonate, potassium nitrate, and ammonium chloride. However, for ammonium chloride, a 0.6 gram sample was used rather than a 1 gram sample. Data including the weight of the samples and electrical conductivity of the solutions were also recorded in a data table. Then, we tested for the electrical conductivity for 3 more reagents. A graduated cylinder was used to obtain a 25 milliliter sample of ammonia, and its electrical conductivity was measured and recorded. The same was also done for hydrochloric acid and hydrogen cyanide. In the bottom left, a data table is included recording the sample size, conductivity, type of electrolyte, and type of compound for various aqueous solutions. And in the bottom right are the balanced chemical equations for each of the solutions. Some potential sources of error for this lab were inconsistencies or discrepancies when scooping sample sizes, weighing the samples, or potential errors that may occur from lab software and operating system. That will conclude our final project. Thank you for listening.